Okay, so our last example should increase the complexity a bit of our feedback control. So far we've seen that we can apply static rules to our particles, where the particle responds to the environment somehow with some fixed rule, or responds to other particles. And now we don't want to define the rules anymore. We would like the particle to learn a rule itself, and that is the application learning swimmers here, where I've depicted a kind of baby, which is our swimmer now, which experiences the environment in some way and learns from its experience to do certain actions or to do not do certain actions, which is even more important, right? So the specific type of learning we would like to have a look at is really also leaned onto the learning of humans and other animals. It's called reinforcement learning. There are a number of papers also how reinforcement learning probably works in the brain. But here we just want to have a look at the mathematical foundations of a specific type, and then also at some realization with the help of swimmers. So the foundation of that reinforcement learning is actually a Markov decision process. So a random selection of a path here between individual states. So along this path, there are these states as 0 up to something until you eventually reach some kind of goal. For example, that kind of pizza, which the baby without teeth can probably not eat, but I can eat that. Yeah. So you have this sequence of states where you go through, and that means for that kind of sequence of state, you can collect a certain amount of rewards. And that's the thing behind this method of semi-supervised learning. You don't give kind of training examples here, but you give a certain reward, what is good and what is not good. And the sequence of these rewards is the total reward you can obtain. So you start here at that point, and that would give you a certain reward from that state as 0. And in the future, you would go through a state as 1, which would give you a discounted reward, R of S1, and so on and so on. And the discount makes sure, so this is a number from 0 to 1, that what you currently have is more important what you get in the future. Your current money is better than the future money, so therefore you discount future rewards here. Okay? So a sequence of such states where you go through and actions you take is actually called a policy, which is denoted here with a pi. So this particular way is belonging to a certain policy, and in that policy you get a certain total reward from which you can calculate the expectation value. You don't have to go always the same path, and that kind of expectation value, under the condition that you start in A0 and A0, will give you the value of that state and that action in this kind of variable q. So the q belongs to the policy pi, which you selected here, and gives you the value of that action in that state here, right? So not all actions and states have to have the same value. There might be one which maximizes this reward. So which maximizes actually this kind of thing here, Q, P of S and A. So this kind of policy which maximizes the value Q is actually the optimal Q or the optimal value of that action in that state. And the policy which belongs to that optimal Qs here is the optimal policy. So this is just meaning you select the best action always for these states from that best value here. Okay. So this is a reinforcement learning procedure based on rewards which are given or which you experience as positive or negative, then it's a penalty. And this is reinforcement learning. Okay, so how would you translate it into some kind of procedure that you can use in a computer to control your active particles? And there are a number of methods actually, but one of them which we can use and which is especially applicable if nothing is really known about the system in great detail, about the physics in the system at least. This is model-free learning, as we call that, is Q-learning. So in Q-learning, you update the value of a state and an action, so this kind of pair, according to that iterative procedure. So if you are at time t now and are in a state S and would like to carry out an action A, then you have a current value of that kind of state action pair, and that is updated now at this time t with a certain reward you obtain for that kind of state, plus a certain value of the next rewards, which is actually stored in Q again, as we've seen before. But for the next state you are entering and the best action you can take in the next state. So A prime and S prime are denoting the next state in which you go, and the best action you can take there, and this is ensured here by this max. So these are the future rewards, and you discount them again by this kind of gamma and subtract the current value in the current state. So if you multiply this whole sum of these three components with a learning rate, which is also a value between 0 and 1, you just add a tiny little bit. If this has been positive, then you add some positive value to the current state and the action, because that helps you to get to your goal. If this is negative overall here, so if it's getting worse, then you subtract something from that and the value decreases. So by that you have a cumulative memory of what action in this state has been valuable or not for the future, right? Okay. So this is the Q-learning procedure we are going to apply, and there are also others which are called policy iteration, and we'll shortly talk about deep reinforcement learning as well. So this is these are techniques often applied also in gaming, for example. So really, reinforcement learning is not really an easy technique. Also, the procedure we have looked at is very simple, but it could be also very complicated. But it's applied to robotic systems, for example, here to the flight of these helicopters or other robots, or it has been applied, which is probably most famously known, to the AlphaGo and also the Atari games, but in a version where you do deep reinforcement learning. So you just directly put in images like that here. So there's a big history of reinforcement learning, and you can have a look at these kinds of citations here if you want to have a deeper look. How do we implement that now with our swimmers? So first of all, we have to define a world and what we would like to learn. And this is now done in a kind of virtual way. So our agent is still our real world swimmer, which is embedded somewhere in a liquid, and you can move them around with the lasers and the control techniques I showed you. But the world is completely virtual, and we separate our sample region into a number of different cells, which is in general called the grid world, and each individual cell is a state in our reinforcement learning procedure. So we have 25 cells here on the board. In the middle, one goal state. We would like to go there, and the swimmer should learn how to reach that goal state as quickly as possible. And there are, I think, 49 environmental or boundary states which are just there that the swimmer learns not to go there, not to leave the board in a way. So in each state there is a number of actions which is possible. In our case, we've selected historically actually 8 of these different actions. So you can go in that direction, up, down, diagonal, left, and so on and so on. And we do that by placing the laser at a certain position. And once you are in that state, you of course have to move quite a while until you transition to the next state. So you do many steps before you transition to the next state. And that kind of transition to the next state is called a transition. It's a state change. While you're moving in that kind of cell, it's not a state change. And when you leave the board, either to the boundary states or you reach the goal, then an episode ends, and then you place the laser somewhere or the particle somewhere here randomly on the board again, right? So for each of the states, we define a reward or a penalty. So in all of the blue regions, you have a penalty of -1. That is there because you don't want to go long time up and down before you reach any kind of situation where you go there. So you want to have a short path. And in the boundary states, you have a strong negative penalty, -100 typically, which should prevent that you fall off the cliff. And then you have a tiny little positive reward here. And this is the setup for our experimental grid world, and then we apply this kind of update scheme of the Q matrix. So in a real world loop, this looks like the following way. So first of all, your swimmer is somewhere, and you have to define in which state you are, that you update the right Q matrix value, right? So you determine now you're in state Sj, and the next thing is you determine the action which you are going to take. So the action which you are going to take is either the best action, which has the biggest value in Q, or it is a randomly selected action, right? So we take typically 80% of the times we choose something, the best action, and 20% random action. And this is called epsilon greedy policy because it allows you to get out of states where you got stuck with a Q value that is unfavorable and by this kind of random choice. So once you've selected that action, for example, this kind of action, you apply that action. You apply that action until you make any kind of transition. So normally this particle would go now horizontally until it traverses to the next state Sk, right? Then you've made a transition. Then you get a reward, and then you can update the Q matrix of this state here initially, because that made you create a kind of reward for this given type of action here to the state K. And after you've updated the Q matrix and you are in the new state, you go there again and do that whole kind of procedure again until an episode ends, either with leaving the board or reaching the goal state. So by doing that, you in principle propagate the positive reward backwards into the whole arena from the goal state. So how does that look in an experiment? In an experiment, you start with that initial Q matrix. You see that it has 8 values here at the boundaries. The one in the middle doesn't count. And the lighter the color, the bigger is the Q value of that kind of action. So diagonal left up is here most likely. Down here is most likely in that next kind of state. This is the goal state. So this is a representation of your initial brain of what you've learned, and that just tells you the swimmer is completely stupid. And then you start the procedure of exploring the environment here. So this is the policy which belongs to that actually. So you see here the arrows of the actions in which you should move, the best actions currently. And the particle accordingly does this kind of strange motion. So it's not really going somewhere. It only eventually reaches here that goal state. So this is one of the trajectory and another one on the backside. If you do that now for a while, 4,800 episodes, which takes roughly 7 hours of learning overall with different speeds and things like that, you see that the trajectories evolve to a straight trajectory towards the goal state. So apparently the behavior is changing really, and that's what you also see in the movies. So no matter where you start, you always end up at the same place. And you also see that your final Q matrix now got a lot more structure and contains some information. So this is all the valuable information you have extracted from all of your moves on the board. And that's the policy which now clearly looks as if you would be pushed here towards that goal state. So this is what you learn finally, and you can measure that you've learned something, and you really end up with something converged if you take the sum of all of these Q matrix entries as a function of time. So here's the sum of the Q matrix entries. And you see this converges into something which is coming closer to that optimal policy which exists here for the given system. You see that convergence also in the transitions, the number of transitions you are taking towards the goal. So at the beginning, you still had 600 transitions on average. Finally, you take less than 100 transitions after you have had 400 episodes or so. So you can apply that learning now to all kinds of situations, and I just want to show you some examples. Here's an example where you go around a virtual obstacle into a goal state, so you really have to find your way around that. Here's a trajectory that you can actually do that. Or you can do that with multiple swimmers, which is in particular interesting because you can share now kind of information or create some collective information or collective learning. So there's the possibility that both swimmers share the same Q matrix, and then learning, of course, is twice as fast because this swimmer is giving information to the other one and vice versa. But you can also supply collective goals. So only you learn something if both swimmers end up in the goal, which will, of course, prolong your learning procedure quite a lot. So these are all possibilities you now have to explore different kinds of information sharing. So there are a lot of interesting things coming out of such studies, and I don't want to show you all of them. But one particular note, which I also don't want to go into details, but I at least mention it, is that the path towards the goal is, of course, noisy. So if you start here in this kind of state, you would go the way towards the goal in the final policy, the different path would look this way. So even you start here somewhere, sometimes you take this kind of route, and sometimes you take a different route, right, in that kind of system. So the trajectories are really noisy, and so it seems that it would be good actually if you go really very, very fast to make everything deterministic. So if you take very fast, then the noise is not playing that kind of an important role, and you will end up straight here on the top. Well, this is not really the case, and this is quite interesting. And to shine a bit of light onto that, you see here this kind of other representation of the Q value of a certain state and action for a given policy. And that is given by a certain reward again, and the discount factor, but then also over a sum of different states, next states again, and next actions you can take under this kind of policy, multiplied with some transition probability. So if the transition probability tells you that you always go here to the right, then this is 1 and all of the others are 0. So there's no transition probability to any other state, then the sum reduces to a single value. But in general, you can have a certain transition probability. And that transition probability now is the thing which contains the physics in our system, because the noise here is the Brownian motion, and that is described by the physics in our system. So you can also represent it like this. You can measure actually that kind of transition probability by starting somewhere here at any kind of point and then measuring if your particle ends somewhere there, and then you measure the probability to end really in that state if you take that action in the horizontal direction, and that will go somewhere here. Yeah? And so that tells you have to understand the physics to understand why it's probably not good enough to go that fast, really fast, to get deterministic motion. And the physics is like this now, and it comes back to what I've explained to you all the time, is that you have a feedback loop and it has a finite time resolution, and that creates some errors. And these errors are not only there for our feedback system, they are there for each kind of feedback system. Bacteria does that in an equivalent way with different parameters, but it does that. So the arrow is introduced now, in our case, again, you observe that kind of particle, you start to decide that you would like to heat it somewhere here to propel in that direction. But at the moment when you apply the action, a certain time delta t has passed, the particle is at a different point, you put the laser still there, and that means you move to a new position. In a new direction. And that kind of directional uncertainty looks like that here. So you have a kind of opening angle of directions and also different kind of speeds in which you go. And that kind of opening angle is causing now that in this direction and in that direction, perpendicular to the motion you actually want, there's also a velocity component. It's an active particle motion which broadens the direction, or here the directions in that kind of direction, in the y direction here especially. And that is roughly the thing which plays an important role. Here you see the experimental measurement of that. You get that kind of point cloud, and it tells you there's some kind of directional uncertainty of your propulsion due to the delayed action. And that delayed action actually tells you, and that uncertainty tells you that a speed limit is probably better than an infinite speed, because in that direction the uncertainty grows much faster than in the horizontal direction, and that's something which seems to be important also for bacteria and any kind of other species. Okay, so that should be just a really brief overview of what you can do with reinforcement learning here in that case. And of course, there are also directions where to go from there. So far, what we've seen is that we can have a discrete space, a discrete state space here of 25 states. If you really want to make that state space very large and even have multiple particles learning, that problem creates huge state spaces which you don't want to deal with in that kind of procedure. So what you should go to is to a continuous state space where you can take any kind of position on the board and get your action from that. And that's done in deep reinforcement learning. So that's a version we've implemented so far, where you have the x and the y coordinate, which is still determined from the image, which goes into a hidden layer and then into an output layer, which tells you about the action. And then you make an update of the weights here according to if the action had a value, a good value or not. So this is called deep reinforcement learning. And you can even do that with the help of the images. So you don't need the inputs anymore. You can directly supply the images. But all of that deep reinforcement learning requires additional techniques to converge, and these are called experience replays, so where you memorize all of your previous things you did. It's like you dream during a certain time, and that is quite time consuming and also memory consuming, so that we did not succeed to do that with images, but we can do that of course with the coordinates, right? So you want to go in this direction and use this kind of technique for more complex scenarios. And one of the complex scenarios is getting away from that virtual environment. You would like to put that into a real environment where your particle learns something about the real structure and can respond to that. And there are even nice theoretical demonstrations, for example, of the Bevan group, where they developed schemes how to react on obstacles even if you don't know the environment before. But you could also go into real physical situations and don't simulate it before. Here's an example where we started to teach the particles to kick a passive particle collectively so that they can somehow a circle here, this kind of passive particle, to move it somewhere, and that is the goal you define. So there are a lot of possibilities, and that could help you actually to understand how certain behaviors really involved which you observe in nature, if you can somehow mimic the environment in your system. So with that, we are actually done. This was the last application I wanted to show you. I hope I did not tease you too much, and we have someday a nice discussion. So thank you very much for listening, of course.